Threads and Spinons Theory, a new perspective on the proton structure. Introduction. The conventional model of the proton describes it as a composite particle made of three valence quarks bound together by gluons within the framework of quantum chromodynamics, QCD. However, this model relies on abstract concepts such as color charge and virtual particles, complicating the fundamental understanding of particle structure. The Threads and Spinons theory provides a novel approach by redefining the proton as a configuration of continuous threads and dynamic spinons, eliminating the need for fractional charges and virtual interactions. Threads and spinons in proton structure. According to this theory, the proton is not composed of discrete quarks, but rather an intricate, self-contained loop of a fundamental thread. This thread forms a stable, closed structure due to the interplay of its own tension and the rotational dynamics of spinons, which are localized energy concentrations along the thread. These spinons move in synchronized rotational states, giving rise to properties traditionally attributed to quarks, such as charge and mass. Thread tension and proton stability. The tension in the fundamental thread governs the proton's mass and structure, ensuring that it remains stable without the need for external confinement forces such as gluons. Spinon dynamics and charge manifestation. The proton's charge emerges from the rotational behavior of its spinons, which maintain a stable orientation that results in a net positive charge. Proton spin and angular momentum. Instead of being derived from the sum of quark and gluon spins, the proton spin originates from the collective rotation of its spinons along the thread loop. Mathematical formulation. The fundamental governing equation for the proton in this model is derived from the thread tension equation, where the charge of the proton is determined by the net rotational state of the spinons, given by where. Experimental. Predictions and comparisons. This model offers several experimental advantages. Charge distribution. The spinon-based charge generation predicts a more continuous charge distribution rather than discrete point-like charges. Proton stability. Unlike QCD, which relies on complex interactions between quarks and gluons, this model naturally explains proton stability through thread tension. Spin. Composition. The total proton spin emerges from a holistic thread rotation, rather than from individual quark contributions, potentially resolving the proton spin crisis observed in deep inelastic scattering experiments. Conclusion. The Threads and Spinons theory presents a revolutionary perspective on the proton structure, eliminating the need for quarks, gluons, and color charge, while providing a more physically intuitive framework. Future experimental validation could focus on high-precision measurements of proton charge distribution, spin behavior, and energy interactions to confirm the theory's predictions. This model offers a promising avenue for unifying particle physics with a more fundamental underlying principle by redefining the proton as a dynamic structure of threads and spinons.